Next paper involves collaboration between scientists at the University of Cambridge and the Fritz Haber Institute for the Max Planck Society. The title is Role and Structure of carbonaceous materials in dehydrogenation reactions. And the paper will be presented by James and McGregor from the University of Cambridge.
Thanks very much. Good afternoon, everybody. Today I'm going to be talking about coke in dehydrogenation reactions, specifically the structure of this coke and the role it actually plays in these reactions. So the reaction that I'm going to be focusing on predominantly is the non-oxidative dehydrogenation of butane over vanadium alumina catalysts. Now the key point here is that this is the non-oxidative reaction. So there's going to be no oxygen present in the feed stream of the reactions that I'm showing. Now, we're all familiar with the idea that carbon laydown occurs in these types of reactions. And this carbon laydown is associated with coke deposition and ultimately with catalyst deactivation. But the question I'm posing here is that neat carbon always have a negative impact in these reactions. Now, obviously, I'm going to try and convince you that the answer to that is no, but for the moment, we'll just leave that as an open question. However, in order to actually address that point, we're going to have to actually characterize our coke that actually forms. And that's what I'll talk about in the second part of the talk, where I'll introduce a technique that many of you won't be familiar with, which is terahertz time domain spectroscopy. And we'll look at this applied to the characterization of ordered carbonaceous materials. Okay, so why are we looking at the dehydrogenation of light alkanes? Well, fairly obviously, we're looking to produce olefins because olefins are obviously precursor molecules for your plastics and your polymers and so on. So the figures in this slide here just give you an idea of the sort of demand for, in this case, propene and butadiene, and also an idea of the extent to which the alkanes are used as feedstocks for these sort of molecules. And the image on the right there is just of an industrial alkene dehydrogenation plant. So, I mean, this is big, large-scale industrial process. However, the industrial process is not without its limitations, if you like. So if we just take the catadiene process as a stereotypical example, this uses a chromium alumina catalyst. However, this catalyst actually deactivates after around 10 minutes on stream, and the reason for that is due to the heavy coke deposition that occurs in this reaction. So that gives you some idea of the problems coke can cause in these sort of systems. So I'm not looking at chromium alumina catalysts, I'm looking at vanadium alumina catalysts. And as we know, these are going to be excellent materials for carrying out dehydrogenation reactions. Now, ourselves at the University of Cambridge, along with the Fritz Haber Institute in Berlin, Peter Stayer's group at Northwestern University in Illinois, and David Jackson's group at the University of Glasgow in Scotland, were part of a consortium that spent a lot of time looking at the use of vanadium alumina catalysts for butane dehydrogenation. And among the results that came out of that consortium were, for instance, the development of structure-activity relationships, identifying the actual role of individual types of surface vanadate species actually on your support and linking them into actually specific catalytic activity and specific catalytic cell activity. However, one of the more sort of interesting results that came out of that was the fact that this was work actually done by David Jackson at the University of Glasgow. And what his group found was actually the main cause of deactivation in these reactions under the conditions that we looked at them wasn't actually the formation of your large polyaromatic coke ensembles, although you did actually form these. The actual main cause of deactivation was the retention of actually tightly bound reaction intermediates on your catalytically active sites. And actually, if you remove these tightly bound reaction intermediates, leaving behind your large polyaromatic coke ensembles, you could actually recover the bulk of your catalytic activity. So that perhaps gives us the first insight that perhaps coke isn't quite such the bad guy that we were thinking it was before. Okay, so on to the present study. This just shows our experimental setup that we're using, fairly straightforward flow-through reactor there, and just some results there looking at the yield of our C4 hydrocarbons. So these are going to be our butenes and our butadienes as a function of time on stream at 550 and 625 degrees Celsius. And what we see in both cases there is exactly as we'd expect, deactivation of the catalyst as a function of time on stream. And this is going to be due to the deposition of coke on the catalyst and the retention of these tightly bound reaction intermediates that I was mentioning before. I've put up yield here, equally I could put up cell activity or conversion, and we've just seen a similar deactivation profile. However, if we go to a higher reaction temperature of 700 degrees Celsius, and this is a notably higher temperature than even the industrial processes run at, what we see is something really quite different. Instead of deactivation of the catalyst after about an hour and a half on stream here, we seem to reach some sort of steady state where catalytic activity doesn't drop off at all, and indeed it's actually much higher than it is at the lower reaction temperatures. And again, we're looking at yield here, but I could have put up cell activity, and we've seen very high steady state cell activity or very high steady state conversion. So that's really quite surprising. And it really almost begs the question, well, the catalyst isn't deactivating, so is coke actually forming at this temperature? And if it is forming, well, what on earth is it actually doing? Well, the first of those questions is pretty straightforward to answer. So here we just have a pair of electron micrographs of catalyst particles after reaction at 550 and 700 degrees Celsius. And what we see in both cases is the presence of significant amounts of carbonaceous deposits on the catalysts. So at 550 degrees Celsius, we see areas of fairly graphitic, highly ordered coke, areas of more amorphous coke, if you like, and areas of the catalyst surface with no coke on it whatsoever. At 700 degrees Celsius, what we see is something quite different. All the coke is very, very highly ordered and exists as these stacked graphene-like layers, as we're sort of highlighting there. And you can actually follow these graphene-like layers all the way around the catalyst particles. And what you see is the catalyst particles are entirely encapsulated by these carbonaceous deposits. So there's absolutely no free vanadium aluminosides for incoming molecules to actually react on. Yet despite that, the catalyst is highly active. So that seems to suggest that the catalysis must actually be happening on the deposited carbon. Now, you might be quite sceptical that carbon can actually do that catalysis. We were certainly initially sceptical. But one way to demonstrate that it can is to compare our vanadium alumina catalyst here with two different carbon nanofibers, just labelled A and B here. And what we see is the activity over the nanofibers is actually very, very similar to the activity we see over the vanadium alumina catalyst. So this tells us two things. It tells us, first of all, that carbon can do this chemistry, and secondly, that it probably actually is the coke that forms on the vanadium alumina catalyst that is actually catalyzing the dehydrogenation of our butane. Another key point to note here is that we do need a catalyst in this system. If we don't have any catalyst, we don't see any gas phase reaction going on, even at the 700 degrees Celsius. So we seem to have identified that we have this, what I'm terming here, active coke. So obviously, we want to actually characterize this material. So we've done that using various techniques, both at Cambridge and at the Fritz Haber Institute in Berlin. And what we see there, common conclusion from all these techniques, is that the coke that forms at the higher reaction temperatures is much more extensive and more highly ordered than the coke that forms at the lower reaction temperatures. However, one caveat here is actually accurately discriminating between actually very similar graphitic materials that perhaps have slightly different catalytic activity is actually really quite difficult. So that's where hopefully terahertz time domain spectroscopy is going to come in and actually be able to help us in discriminating between these different carbonaceous materials. So most of you probably won't be particularly familiar with terahertz time domain spectroscopy. So terahertz time domain spectroscopy was first demonstrated a long time ago in a galaxy far, far away. I do apologise for this slide, but apparently Lucasfilm is only 10 minutes down the road from here. So if you believe everything you read on the internet, then this Star Wars character has a terahertz radar in his helmet that he can use to identify alien species. So how would that actually work? Well, this is where terahertz actually sits in the electromagnetic spectrum. So it's there sandwiched in between your microwave region and infrared radiation. And this just shows the sort of vibrations that occur with this sort of characteristic frequency. So in our case, the sort of thing we are going to be most interested in when looking at coke are going to be these phonon vibrations here. So in the sense of sort of graphitic type coke, terahertz is then going to be sensitive to the motion of bound electrons within graphitic phonon modes. Terahertz is also going to be sensitive to the actual density and mobility of free electrons in your coke as well. So it's essentially going to give you a measure of the conducting or metallic character of the coke. So really the key thing to note here is when we go off and look at our terahertz spectra, when we see higher absorption, that's going to correspond to coke that's more highly ordered, more conducting, and possibly also in larger domains. So here we just have some terahertz spectra of our catalysts after reaction at various reaction temperatures. And first thing we see is at temperatures that are below 600 degrees Celsius, we don't really see a lot. However, that's actually not a problem, because at this temperature, the coke that forms isn't actually that highly ordered, it's not too graphitic. And we can use more traditional techniques to probe it. So for instance, we can look at these cokes quite well by NMR spectroscopy. Above this temperature, however, the cokes that form actually become conducting. And you can't look at conducting materials by NMR, but that's where terahertz really comes into its own, and we're getting quite good discrimination between these carbons that form at the higher reaction temperatures. So having identified that terahertz is pretty useful for actually looking at these structured carbonaceous materials, we begin to ask if we can then use it to look at things such as carbon nanotubes and carbon nanofibers. So these sort of materials are pretty well established to catalyze the oxidative dehydrogenation of ethylbenzene through to styrene. Now, this is notably different from the reaction I was talking about before, because we now do have oxygen in our feed stream. And the oxygen in the feed stream here is pretty crucial, because it's actually the interaction of oxygen with defect sites on the surface of your nanostructured carbon that actually create the selective sites for the formation of styrene. So what we're looking at here are 3 different carbon nanofibers, which have been prepared at temperatures ranging from 973 up to 3,273 Kelvin. Now, the temperature of this treatment affects how graphitic the outer surface of the nanofiber is going to be. So a higher treatment temperature is going to create a more graphitic sample with less defects. So what we'd expect is that higher temperature treatment should result in a catalyst that's actually less selective, because it's got less of these defect sites which interact with oxygen to create selective oxidative dehydrogenation sites. And that's exactly what we see when we look at our catalytic data. The material prepared at the lowest temperature gives us the highest selectivity, and that prepared at the highest temperature gives us the lowest selectivity. Now, if we actually look at the terahertz spectra of these materials, what we see is something that actually agrees very well with this. So, for instance, if we take the material prepared at the highest temperature, which we're expecting to be the most graphitic in nature, we see this has quite clearly the highest absorption. Conversely, the material prepared at the lowest temperature has the lowest absorption, because that's the least graphitic material. Now, all of that's fairly qualitative, but as you can see, we have applied model fits to these data. The first one there is an MG fit, which stands for Maxwell Garnett fit, and VR fit, which is a Bruggeman fit. I'm not going to go into the mathematical details of those fits. The mathematical details are in that JFIS Chem C paper there. All I do want to do is actually highlight 2 of the 7 parameters that are fitted in these models. And both of these parameters focus on the actual free electron density in the nanofibers. And what you see is as we go from the material treated at the lowest temperature to that treated at the highest temperature, our free electron density is clearly increasing. So we're actually putting numbers to these terahertz spectra. So that's really all I want to say. I just want to finish up with just one slide of conclusions. What we've seen is that coke that actually forms in situ during butane dehydrogenation over vanadium aluminum at high reaction temperatures is actually active for catalyzing the dehydrogenation reaction itself. And that's notable because if you think of the catalyst in the industrial environment, when it's run at a lower temperature, that catalyst actually deactivates very rapidly because of carbon buildup. And our reaction is also very highly selective. And we've also seen the development of terahertz spectroscopy to study these ordered carbonaceous materials. And we've made the first steps towards actually correlating our spectroscopic data with our catalytic data, as we saw for the ethylbenzene reaction. With that, I'd just like to thank our co-authors, both at Cambridge and at the Fritz Haber Institute, funding bodies, David Jackson and Peter Stayer, for their valuable input into this project. Thank you.
Okay, we have time for some questions.
Olaf Deutschmann, Karlsruhe, Germany. The question concerns a relatively high temperature, 700 degrees centigrade.
Yeah.
Is there a possibility that you get dehydrogenation in the gas phase as well, pyrolysis process at these temperatures?
You do need a catalyst to be present, but is there a possibility that something's happening, a process happening on the catalyst that then generates a species that reacts in the gas phase? I wouldn't be able to definitively rule that out, but you do need some sort of catalyst to be present, yes.
You may do some blind experiments just at the same conditions, check out the gas phase temperature, gas phase reactions do not play a role.
Yeah.
Yes, next question.
In your presentation, you use terahertz as a method to characterize the degree of gravitarization of this carbon material.
Yes.
Usually people use Raman spectra to see this, so can you compare those 2 methods?
Yes. I think, well, actually, I've probably got some. There's actually some Raman spectra of, this is the coke that's formed at the 2 different reaction temperatures, for instance. And there's not a great deal of difference if you take the ratio of your sort of G and D bands in that. The main difference that you're seeing is when you go to the more graphitic material is the sort of narrowing of the line widths. But you're trying to pick up relatively small changes. And there are some issues with using Raman. For instance, you still get your G band, even if you've only got benzene type materials, which clearly aren't graphitic. So that is what people normally use, but it's not that straightforward, and sometimes it's pretty tricky to interpret, whereas the terahertz does seem to give us a much more straightforward to interpret set of data.
Yes, we have time for one short question.
Did I understand that when you went higher in temperature that things got worse again, above 700? I thought you had a slide about higher.
I didn't go to higher than 700 degrees Celsius.
So it just got better at 700?
Yes. I don't know what happens if you go higher temperature.
Okay, yes, we have time for one last question.
Yeah, I have 2 questions. First question is the same as you.
Well,
I just
same
wondered
answer.
about the 700. So, the observance of terahertz, the signal is associated with the conductance and the order.
Yes.
Order. So, the most other that I can think of the coke is graphite. So what's the compared to signal terahertz signal of the graphite? What's your sample signal? It's similar, or what in each kind of degree of the how similar in terms of other needs with graphite?
We haven't actually looked at graphite. We are looking at some HOPG actually at the moment, but we haven't got that data yet. But the nanofiber that's treated at 3,000 Kelvin is going to be pretty graphitic on the Earth's surface. But yes, we do need the sort of standard to compare it to, and the standard would be HOPG or something, and we are doing that experiment just now.
Okay.